An action called reduce reduces the entire RDD into a single value. For using reduce, we first need to define a function which merges two elements into one. This function must take two arguments and return a single value. The arguments and return type should have the same data type. Then we call reduce on an RDD with this function as argument. Let's take a look. We log into CloudXLab Web Console, start Spark-shell, wait for prompt to appear. Let's create an RDD SEQ by parallelizing the array having numbers from 1 to 100. Let's define a method sum with two integers as arguments and returning an integer. It returns the sum of two arguments, x and y. Let's check if this function is working. It is a scalar function and it does not depend upon Spark. You can see that calling sum on 1 and 3 has given 4 as result. Now let's call reduce with this function sum as argument on SEQ RDD using seq.reduce bracket sum bracket closed to a local variable total. Let's check the value inside total. You can see that the total is 5050, which is summation of all the values from 1 to 100. To confirm, you could also use the formula for summation of natural numbers n, which is n into n plus 1 divided by 2, which equals to 100 into 101 by 2 equals 5050. The function that we defined only takes two arguments, but the reduce is able to convert the entire array, irrespective of its size, into a single value. How did this work? Answer is very simple. Reduce action has called the function sum again and again, combining the values and the results of previous calls into a single value. Say we have an RDD of integers having two partitions. First partition having values 3, 7, 13 and second partition containing 16 and 9. We want to compute the sum of the integers. Our sum function will be called on 3 and 7 first, and then the result, which is 10, will be added with 13 in the second call of sum. Thus, sum of the partition will be 23. Parallelly, the second partition will be evaluated. The sum function will be called on 9 and 16, resulting in 25. Now the partition 1 has been evaluated to 23 and partition 2 has been summed up to 25. Both of these computations are happening inside two different Spark applications, which might be running on two different CPUs or different machines altogether. Now the values 23 and 25 will be summed up in a next call of sum to give the final value as 48. This would be happening in Spark driver. If you are using a Spark shell itself is the driver by default. So, our sum function has been called 4 times. Twice in one Spark application, and once in another Spark application, and once in the driver. This is how Spark distributes the processing under the hood while you are simply executing rdd.reduce with your function. The way we had computed summation using reduce, can we compute the average in the same way? Let's try. Here, we have created a function avg that takes numbers as argument and returns the average, which is of double data type. Please note that the data type of return as well as the arguments need to be same because the output of one call might be fed as the input to another call. So, we have kept the data type of arguments as double too. Let's call reduce with our average function. The result is wrong. It is 9.875, while it should have been 9.6. Also notice that every time you call the reduce, it might give different results because the output is based on in what order the average of element is computed. Why is the result wrong? Let's try to see what will Spark do under the hood. As you can see in the diagram, the average of 3 and 7 is 5, which is correct, while the average of 5 and 13 is 9, which is incorrect because it should have been 3 plus 7 plus 13 divided by 3, which is 23 by 3, that is 7.67, not 9. So average of 3 numbers is not same as the average of averages of 2 numbers at a time. But sum of the numbers is always same, no matter in what order you apply the addition or which pairs do you pick first. This property of operators or functions is known as associative and commutative. A reduced function must be commutative and associative. Otherwise, the results could be unpredictable and wrong. If changing the order of inputs does not make any difference to the output, the function is called commutative. The valid examples of operations having commutative property are addition. Whether you add 2 to 3 or 3 to 2, the answer would be same. Same is the case with multiplication and average and Euclidean distance. The distance from point 1 to point 2 would be same as point 2 to point 1, though that's not true in case of one-way lanes in the cities. The example of operations which are not commutative are division, subtraction, exponent, or power. The associative property states that you can add or multiply regardless of how the numbers are grouped. By grouped, we mean how we use parentheses. In other words, if you are adding or multiplying, it does not matter where you put the parentheses. You can add any parenthesis anywhere you like in an expression containing only addition or only multiplication. The example of operations with valid associative property other than summation and multiplication are max and min, multiplication out of 3, 4 and 2, whether you first multiply 3 and 4 or you first multiply 4 and 2. The result of multiplication will always be same, which is 3 into 4 into 2 equals 24. Similarly, minimum and maximum functions yield same results no matter which two elements are compared first. For example, whether we compare 3 and 4 first and then compare the result with 30, or compare 4 and 30 first followed by comparison with 3 would yield the same result. Here are some examples of functions which are not associative. Division. If you divide 2 by 3 and then divide the result by 4, the answer is 0.67. If you first divide 3 by 4 and divide 2 by the result, the answer is 2.7, which is a huge difference. Similarly, subtraction 2 gives different results if the groups are changed. We have already discussed average, that average yields different results if called on different groups of values.